Welcome back, everyone. So our last speaker for today is sorry for my.
No, it's good.
So he's talking about I don't remember the title, but certainly extremely interesting to my opinion. May write the title if you want, so
Okay.
I can read it.
Okay. Anyway, it's towards classifying CFT in 4 minus epsilon dimensions.
Okay, so Junchen instead about
Okay. Yeah, I understand this is a mixed audience, so I will introduce a lot of things. So basically, this is a work towards the classifying of CFTs in a certain corner. I guess for many theoretical physicists, it's a dream to classify CFTs, right? To know the space of CFTs. But unfortunately, this is only possible in some very limited corners. For example, one corner is like in two dimensions. You can work with more mass structure, the representation theory of Will's-Arrow algebra, bias average, and then you do some bootstrap-like approach. You will be classifying a special type of CFTs in 2D. That's one corner. Today, I am going to talk about a slightly different corner, which is in 4 minus epsilon expansion. The 4 minus epsilon expansion is some trick, that physicists use to get a feeling about quantum field theories. It's not completely rigorous, so I will first explain a little bit of the background of what this really is. So let's really just consider a Hamiltonian, a classical Hamiltonian, and coupling neighbors. Many of you may notice this is the famous Eisen model. I define this variable to be on some lattice. Let's see, whatever lattice. On each of these sites, I have a variable which takes value from -1 to +1, either -1 or +1. So you can define a probability measure, basically like this, which kind of like sigma I. And beta is 1 over 30. And this is, we call it potential function, but it's really a probability measure. Well, I haven't normalized it yet, but really it's a function of t. You are summing over all possible configurations of the spin. And using this, you are supposed to calculate expectation values. Because it's a probability measure, you can calculate the expectation value. For example, I can calculate a specific spin defined as, again, the summation of all the this would be the expectation value of my spin at a specific point, right? So if we are smart enough, we would be able to perform this summation completely, right? But it's extremely hard. And we do know what the phase diagrams looks like. So essentially, you have as a function of t over g. This is t is the temperature here. G is the coupling constant in front of this. So there's a special point at some Tc, critical temperature Tc, which a phase transition happens. So basically, above this Tc temperature, we have some vanishing expectation value for the 1-point function. Okay, this this one-point function I defined here is equal to 0. Below that, I have my one-point function to be not equal to 0. And in between, there is a transition, which we care about. It's called second-order phase transition. And for physicists, the second-order phase transition is almost the same as the conformal field theory. So it's described by a CFT. For example, one of the nice behavior is like the expectation value of two spins at this critical temperature. It scales like 1 over I minus G, the Euclidean norm, to some power. It's a power law behavior.
You mean by almost? So if you are complex example?
Sorry?
Second order phase transition, almost the CFT.
Yeah, in some quantum cases, you can have like broken Lorentz symmetry, whatever, exotic cases. Yes, but I mean, for today, we will focus on CFTs. But anyway, this is the story in terms of probability. We can, I mean, there are mathematicians who are trying to prove things using this probability measure, and they do fancy works, amazing, beautiful works. But in general, to perform this integral, to calculate this expectation value is very difficult.
This is valid only for dimension greater than 1 or not?
Yes, this is valid only for dimension greater than 1. So the claim of physicists is basically, I can write this path integral, this measure in a completely different way. Okay, and so now phi is a function in R4, R3, R4 in Euclidean space, and performing this integral over all the functions in this space. This is a scalar function, and this is a functional, and it's basically is the integration. Let's see, d-dimensional integration of phi. Let me use Laplacian. Squared plus a up to the 4th. Okay. But this is a formal like partition function. If we are smart enough, we should be able to calculate, really perform this integral, and evaluate it in terms of a function of a and lambda, its couplings. But no, but I mean, up to now, I don't know any ways of actually doing it. Yeah, but we can, for certain corners, we can actually do some calculations and get a feeling about what this path integral actually tells us. So I'm going to give some hand-waving argument. Basically, I do a Fourier transformation of my function, and I break it into two parts. Let's see, k for the normal k to be bigger than 1 over L. This I'll call it bigger volume 1 over L. So I break it into two parts. This is a function. This is for the large momentum part. This is for low momentum part. So the argument of Wilson, which he invented in the 70s, 60s, 70s, was that, okay, you perform this integral, you integrate out the high momentum piece, and you are left with a similar action, but only for the low momentum piece, which is still looks like this path integral, but you have a cutoff, which is given by this L. And this, well, suppose you can perform this integral, your coupling constant, this one, they will basically run, they will change this value, it will be a function of L, of this cutoff L. It will run, and it's given by some equations called RG flow equations. So basically, let's see, beta A so my function depends on my cutoff. So it's like a flow equation. As that flow equation on the right-hand side is usually some polynomials. Okay, so this gives me the running of my coupling constant as a function of cutoff scale, which is the momentum I integrated out. Okay, that's a crash course on renormalization. So, but this is as I said, this is not concrete. If you are not really doing it in some very special limits, like for my Simpson expansion or some long-range model perturbative limits. Okay. So, but surprisingly, this kind of hand-woven stuff already is telling us a lot about physical systems, and so when you actually try to perform this integrating out these higher momentum modes, you encounter some integrals. We call it Feynman diagram integrals, and these integrals are not possible to perform when you are in general case, but it's possible to perform when you are close to 4 dimension. So we do this in Formas epsilon dimension, and we try to derive these RT flow equations in Formas epsilon. So basically, let's assume that we already, well, let's just first set this coupling to 0, and our RG flow equation now becomes E lambda in this limit becomes something like this. I think it's lambda here. Okay. So let me draw it. No, positive, sorry, this way. It's lambda. Sorry. So this flow equation tells me that as I change my cutoff scale L, which means that I'm taking this cutoff smaller and smaller, I'm like integrating out everything. I'm left with the final value. So this flow equation tells us, okay, there is a fixed point here, right? So when I integrate out my couplings, my high momentum modes, in the end, I reach my couplings runs into a fixed value. And this fixed value, we call it a fixed point. And in physics, this corresponds to conformal field series in this special limit, in Formas epsilon limit. So this epsilon here is my space-time dimension. So this is already not very concrete because I'm working in Formas epsilon dimension, and I'm taking epsilon to be approaching 0. So that's related. Sorry. Yes, approaching but larger than 0. So actually, I mean, if you actually do it, all the quantities you calculate in this approach, you get some formal series in terms of epsilon, which you have to actually do the resummation to try to make sense of it. It doesn't always make sense, but this limit already tells us a lot, and so my goal is to classify all the fixed points in this Formas epsilon expansion, and therefore to get a feeling about the landscape of CFTs. So let me repeat what I said in the beginning. In 2D, you can, well, because of the beautiful structure with our symmetry, representation series of Illusory algebra, unitary representation, you classify unitary representations, you already have a lot of result, strong coupling result. But this is another corner, which is formality zone. So my hope is that, okay, suppose we are able to classify CFTs in this corner, and we also know the two-dimensional corner, and we can combine these two information and get a good feeling about what happens in 3D, basically. And the reason that I think now it's becoming more and more possible is because this recent development of so-called conformal bootstrap approach. This conformal bootstrap approach allows you to perform, to bootstrap a CFT not just in fixed dimension. You can do dimensional continuation, and maybe you can, if I finish classifying these CFTs, I can also apply bootstrap to continue them from 2D to 4D, and then to to start a 3D results. Yeah.
So if you do 2 plus epsilon, you immediately lose all the irregularities, right?
Yes, right. You can, well, I mean, actually, there's a similar story. You can do basically, you use 2 plus epsilon, you use a nonlinear signal model, and you can classify perturbative fixed points in 2 plus epsilon. Yeah, something like that.
Say that I will see how you can connect the Girasol minimal models.
Yeah, I think usually these CFTs I will discuss, they usually don't go back to minimal model. They go back to some other 2D models, but some cases are clear, some cases are not so clear. So, yeah.
What you are classifying is the one that is accessible by Wilson Fisher.
Exactly.
But CFT, I mean, there is no guarantee that all the CFTs they are accessible by Wilson Fisher, right?
Yeah, precisely. So so I'm doing scalar theory at this moment. So, but well, you can try in the future to add fermions here, to add some Yukawa coupling to add fermions, and you can add gauge couplings and make them charged under gauge field theory, and you again.
Then it will be totally out of the classification.
Yeah, right. So let's focus on scalars for the moment, and maybe in the future projects we can worry about that later.
We should say that when you have, like, of course, in this case, it's perhaps simple, but if you have more complicated models already classifying the fixed points at the first order in the epsilon expansion, it's highly non-trivial. Like, it's a highly non-trivial mathematical problem.
Well, even in this case, it's already. So I'm going to consider not just the one scalar. This case is like one scalar field. I'm going to consider many different copies of scalar fields. So I'll change my action.
For example, angle 4
yeah. For just scalars, but my hope is that this is a long project. Maybe in 10 years we can, not 10 years, 2 or 3 years, we can do that. But let's consider. Okay, so instead of considering just one copy of scalar fields, I consider n copies of them, and I consider the most general lambda-5 coupling. The reason that I think this is a complete project is that, okay, the marginal couplings in 4D are limited. You have like the lambda-5, you have the Yukawa coupling, you have the gauge coupling, and that's it. So if you are powerful enough, you can, I think it's probably can be finished in the future. But let's consider just scalars for the moment. Now, my bit function becomes this. Plus epsilon Okay. Repeated dummy indices are summations. So now it's a tensor, and with Mn being summed, now it's again a tensor with IJKL, right? So this is my beta function, and for physicists, this comes from the one loop diagram basically, and give it to lambda phi 4. This you need to fully symmetrize it and do this. Okay, now it's a task for mathematicians. You can try to solve it.
Finding the zero.
Yeah, finding the zeros. Basically, you set this equal to 0, and that's your problem. So it's actually quite hard, especially when well, I mean, if n is equal to 2. Actually, you can just plug it into whatever software you have, Mathematica. It like pops out immediately. Okay. If it's n equal to 3, it's already pretty hard. And you plug it in Mathematica, you ask it to solve for it, and you start to lose patience, and you don't know whether it finished or not. Okay. So there are essentially two approaches on the market. One is a so-called brute force approach, which is essentially what I mentioned. You plug it in Mathematica, but you do it a little bit more smart, because this is actually a polynomial equation, right? You can, for example, why is it a polynomial equation? You parameterize this tensor somehow, like 1, 1, 1, 1, you call it x1, number 1, 1, 1, 2, you call it x2, blah, 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 blah. And it becomes a polynomial. And there are well-defined approach to solve polynomial equations, which is the so-called Gröbner basis, right? And Buchberger algorithm.
But it's possible that some of the degree of freedom, they are redundant.
Right. So in this case, indeed, yes, we are. I mean, this okay, as Zerhan is saying, this is a equation which respects the ON symmetry, because if you rotate this tensor, if you rotate like I, G, K, L, you perform this rotation, and this R belongs to ON. Okay, and if you have a solution, then rotating by this ON matrices, it still satisfies the same equation solution. So that's why that's what the trend is saying. So basically, you have some redundancy. But let me mention something that okay, so we didn't know that we should use the Gröbner basis before asking it on mass exchange. There's a question asked by Slava Rychkov, answered by Robert Bryant, called the, I think you could search for tensor equations, you would find it. It's a very nice answer. In fact, that answer basically solves the n equals 3 cases. There are a few gaps which you need to fill in yourself, but that pretty much solves the case. So, but let me give you a little bit of the details, since there are physicists here. So first, as Zerhan is saying, we have this ON symmetry. We have to gauge fix it somehow. So one way to gauge fix it is to let's see, to set equal to G I for all I bigger than G. This is a condition that you add to your equations so that you gauge fix this ON rotational part. You count how many equations you have. You actually have n times n minus 1 divided by 2. This is the same number of the generator. This is the same as the number of generators for one group. So you can kind of expect that after setting this equation, you already would have gauge fixed the solution, and you are going to get like discrete solutions in your system.
Question, but are you imposing this symmetry? Because I mean, you can certainly have.
No, this is a symmetry that comes from the equation automatic.
It's like a field redefinition or something like this. No?
Yeah, exactly. So this is like field redefinition. Yeah.
I mean, you could have, you certainly can have fixed points that break it.
Yes.
So
exactly.
how do you, like, if, but in that sense, if you impose this Fourier symmetry, then,
No, I'm not imposing it. This is the freedom coming from field redefinition,
okay.
right? So,
Okay, understand.
so my solution, of course, would have like smaller symmetries as compared to this. Yeah. So the reason that let me see a little bit words about what the Gröbner basis is, right? It's called there's this concept called ideals. So what is I ideal? It's a subset. Let's call it I, that belongs to, let's not call it R, let's call it F, x1 to xn. And this denotes all the polynomials in this n variables, the coefficients being within some field, let's see, F. And the ideals are defined in this way, in the sense that, okay, the first condition is 0 because belongs to the ideal. This is a number. The number 0 belongs to the ideal. Second condition is like if F belongs to the ideal and G belongs to the ideal, F plus G belongs to the ideal. The third condition is that if F belongs to the ideal and G belongs to this, so this F, whatever polynomials you have, and F times G belongs to the ideal. Okay, why is this important? It's actually really just I mean, I'm looking for solutions to some polynomials, right? If my polynomial is equal to 0, F is equal to 0, my polynomial G is okay. Yeah, let me explain this way. I am going to have a set of polynomial equations. 0, Fn equal to 0. Okay, you should understand this as a generating set of your ideal. So if my F is equal to 0, G is equal to 0 is one of them. Their summation, of course, is vanishing. So if my F belongs to one of this, my G is some whatever a polynomial. You times this 2, it gives you, again, equal to 0. So this ideal would be all the polynomials that vanish on the solution space of this guy. Okay, so to study this ideal basically is to study the solution space of these polynomials. So there is a well-defined approach to study this ideal, to find a good generating set of this ideal, which is called Gröbner basis, reduced Gröbner basis. And in this reduced Gröbner basis, my polynomials looks like this. Let's see if I have like x1, xn as my variable. In that reduced Gröbner basis, my f1 would involve like xn, 0, something like that. But it's in a so-called upper triangular form. Maybe here it's like x1, x2 equal to 0, right? Okay. So mathematician has discovered an algorithm to put this, to start with this, doing these operations, polynomial divisions or whatever. In the end, you put the polynomial in this form, which the claim is that this and this generate the same ideal. So now you can try to solve this system. The algorithm has been invented. It's known to terminate, even though it might take many, many steps to terminate. It's not really efficient. But this is but you can, it's implemented in Mathematical or whatever, Maple, whatever software you like. But this upper triangular form is especially interesting because, I mean, now you can solve this one. This is a univariable polynomial. You solve this, you plug in this one, you can solve this one, and then you do step-by-step approach. in the end, you do that. So how much time? Half hour. Okay. Yeah. Okay. So in that question, basically, Robert Bryant told us you can do this, and you can do this. Indeed, you plug in Mathematica, and now you can convince yourself. Actually, Mathematica is not doing crazy things.
Mathematica as a function to turn that system into that?
Yeah, exactly. Basically called Gröbner basis. Yeah. This is a mathematical function called Gröbner basis.
Okay, so the later one, the FCM also labeled, right?
Yeah. I mean, it's probably not n. You are going to have like more equations, like maybe some number here. But the real upshot is that the last one is univariable, so you can solve and plug back its upper triangular form. If your initial equations are, well, if your solution space are not too complicated, you can do that. Basically, for N+3, you can use Mathematica. You wait for long, but acceptable amount of time. In the end, you get a polynomial for your system. So I can break it into three parts. Like T2. What's a T4? This is a tensor which is rank 2 symmetric traceless. This is rank 4 symmetric traceless. This is a singular part. So you're basically decomposing this tensor into representations of O3, On. And so I chose this S to be the first variable in the Gröbner basis. In the end, you got a polynomial for S. For example, you get something like S 5 S minus 1 for the fourth. Let me not copy everything, but this is one of the Gröbner basis polynomials. This is the last one. So you can see it's a factorized polynomial. So your S value can only take like this limited values. So, and you can indeed check that each of these numbers corresponds to a known solution that has been discovered by people before. They didn't really do systematic search. Well, you start with whatever guess you have, you start to search for solutions, and in the end, you find many. But this is a result basically tells you, okay, now you finish the classification, right? You know, like all the solutions has been discovered, and you can stop searching. You can. That's why I said that's why the talk is about classification of perturbative fixed points. This all works very nicely for N+3, but if you start to really push it to N+4, a lot of the things, first of all, it's very hard because there are many more variables for the N+4 case. So we can do a count, right? N times n+1 times n+2 n+3 divided by 4 factorial. This thing grows very highly, very quickly. This is the number of independent components of this tensor. So it grows very quickly. So for N+3, it's solvable. N+4 is not solvable. In fact, I think it's essentially because I mean, there are many monomials appearing in this polynomial, and their coefficients grows very quickly. There are even subtle issues, like instead of getting isolated solutions, you get a continuous family of solutions even after the gauge fixing.
You mean not solvable in principle, or not solvable due to?
Oh, we haven't solved it. Not solvable due to the lack of computer memory, basically.
But do you expect? So you said that you find a conformal manifold.
It's more subtle than that. So actually, yeah, since you asked, in the Incal4 case, I told you how to do the gauge fixing. That gauge fixing is efficient for the Incal3 case. But in Incal4, even after this gauge fixing, you find continuous parameter family of solutions. But it's even weirder than that. After that, if you check that, you start to calculate like the invariance. Invariance means like things like this: IGKL, IGKL. You find these invariants, they are the same on this full manifold. So somehow these solutions should be equivalent. The reason being, let me see if I can get it correctly. The reason being the actual symmetry of this solution, this equation is not O4R, it's O4C, the complex O4C. So there could be polynomial invariance does not separate orbits anymore for this group. So there could be different orbits, different O4 orbits that corresponds to the same, have the completely the same polynomial invariance. So this is indeed what's happening in this case. And because of this, all these O4 orbits, different O4 orbits, it corresponds to the same solution. They have the same polynomial invariance, and they appear in your system. And basically that stops you from, well, that doesn't stop you, in fact.
Like CFT data will not depend on these parameters.
Exactly. So it looks like it's not conformal manifold. Well, I mean, all the physical spectrum, right? The eigenvalues of the operator spectrum, I think they would algebraically depend on the invariance, because I mean, you expect that after some rotation, you shouldn't change, right? So, so even though you have a continuous family of solutions, you don't find new solutions. So this caused some trouble because, I mean, there is this Gröbner basis approach. We also tried another approach, which is called homotopic continuation. This is what mathematicians again invented, more numerical approach. But that this appearance of this new subtlety making that also quite difficult. So, but long story short, is that the Incal4 problem is still at this moment is quite hard to solve. We are working on it, but hopefully we can report about it more in the future. This is one way, and actually, instead of using Gröbner basis approach or any of your favorite mathematical approach that you guys like, this problem has a easier version, a simpler version, which is that instead of looking for the most generic solution, you can look for a subset of solutions, which we call irreducible fixed ones. So-called irreducible fixed points, mathematically, it basically means that the solution preserves the group G, okay? In this case, this group G has to be a subgroup of On, because On is like your maximal group. And by irreducible, I basically means that the n-dimensional representation upon, okay, n-dimensional representation upon decomposing into this subgroup still is n-dimensional, okay? Mathematically, this is essentially what it means. But, well, this, so my fixed point can preserve some symmetry, some group symmetry, like the Eason model, which preserves Z2, the cubic model, which preserves the sign permutation group in mathematics. And this group would be the groups that your solutions preserve. And this group would be the initial symmetry, which is the symmetry of your solution, of your equation. And this is a subgroup of O(n). So when you look at this vector space, in terms of the small group, it should decompose into irreducible representations of this small group. And I require that the n-dimensional representation, which is we usually call vector representation of O(n), still is irreducible. It doesn't become tooth representation or higher. The reason for this is also physically motivated. So,
can you give me an example of these
yeah, okay. For example, I can see, like, let's see, we start from O5, 5 scalars, and one group is like cubic 5. I think you should really write it like this: Z2 is rest product of S5. And another group, let's consider like O3 times O2. And the 5-dimensional representation in this one is still 5-dimensional. So this is the irreducible subgroup. And this guy would be 3 plus 2, right? So I don't care about this one for the moment. Yeah, for the moment. So the reason is also very physical motivated. So I showed you the phase diagram of Eisen model, which my Hamiltonian is given something like with sigma I takes the value of -1 +1. Okay, it takes the set from -1 to +1. Let's consider a small generalization of this model. -g, still nearest neighbor coupling. But I add another term. But now I allow my spin to take 3 values: 0, -1, or +1. Okay. This is a similar Hamiltonian, but with an extra term. This extra term, my spin now takes 3 values. So now I have 2 couplings. I put a coupling G here. I have 2 couplings. I can ask what is this phase diagram of this guy. Essentially, the phase diagram you are getting would be something like this. Sorry, it should be the other way around. Like this. By solid lines, I mean second order phase transitions, the CFT phase we discussed before. By dashed lines, I mean first order phase transition. But the information here is that along this 4 line, second order phase transition line, it's all given by the Eisen CFT. Okay, it's all given by the same universality class, the same CFT as the original Eisen model. So even you deformed it by a new coupling, you draw this phase diagram. I mean, there's still a codimensional 1. This is a line in 2-dimensional space, so it's codimensional 1, a codimensional critical line, which corresponds to the Eisen model. The reason for this to appear is that the Eisen model has like one, we call it relevant operator. Relevant operator is the type of operator that grows as you go to the infrared, as you take your cutoff to be approaching 0. So its couplings would grow. So the number of like relevant operators in your CFT is extremely important because it tells you the phase diagram. The more relevant directions you have, the more codimension you have in your phase diagram. So essentially, the number of relevant operators is very important. Because of that, I can write down the relevant operators for this coupling. So basically, one of them is this, with summation of I. which I call it the mass term. Okay. But if my group is still irreducible, I can only write this one, right? On the other hand, if my group is like O3 times O2, I would write some two mass terms, M1 squared, 1 to 3, phi 1, phi I, M2 squared, 1 to 2, oh, no, sorry, 4 to 5, phi I. This will be the two mass terms that can appear in my action. So even if I start with this action tuning the mass to 0, after I run the RG flow, I go to lower cutoff, these mass would be generated. So I have to tune them to 0. So by requiring that my n-dimensional representation to be irreducible, I'm requiring that I care about only the systems, the statistical systems that has just one relevant operator, which in the meantime means that I care about CFTs that are easier to access in your phase diagram. Has less codimensions. No, they are independent because, sorry, I didn't make this clear. I'm considering, let's see, the O3 times O2 subgroups of O5. And then this guy is invariant under this subgroup, right? Because this guy just rotates the first three components. And this guy rotates this component. So they are both in like invariants of your system. So essentially, I'm requiring to be reducible means that I'm paying attention to the physically more easier to access like CFTs. So these are the interesting, the most interesting ones. Well, then this becomes a group theory problem, basically, right? So I have a group ON. I have a group ON. I want to find all subgroups of it. How many minutes? 5. Okay. Yeah. So anyway, I'm almost done. So I have ON. I want to find all the subgroups that preserves this condition. N goes to N. And now you can look at the list. Luckily, mathematicians also work on this problem. For O3, actually, I think a lot of us already encountered it in our life. So this is the famous AD classification of the SU2 subgroups or O3 subgroups. If you work on crystals, these are the point groups. For O4, it was also done. Was done in a book. I forgot the name of the book. I think it's quite famous book by P. Duval. This result was used almost 40 years ago by Louis Michel, Toledano, Eduardo Brizin, who is a professor in IHES, to classify the O4 keys. So they basically did this. And much more recently, there is a paper by you can look at the result later, but they classify the O4 quiz. Actually, up to O6, it is known. O6 is known because of this relation to SU4. Okay, and the SU4 subgroups was clarified a long time ago. A famous mathematician. I will not try to pronounce his name. Yeah, so now you can just basically take this group theory results, and you of course you still have to parameterize these invariants and plug in that RG equation and try to solve it. But after requiring this condition, this irreducible condition, it's already the list is not infinite anymore. So any finite groups, subgroups of On is actually infinite, because O2 like contains Zn, right? Contains all the cyclic groups. It's not doable. But after requiring irreducibility condition, you do it. It's already good. So it's a finite list. We recently picked this up and did work for 05, and I won't explain the details. The algorithm was pretty much very similar to what Louis Michel and Franz did, but now we are in an age of computer. So there's a very beautiful computer program called GAP, which basically in GAP you can do everything. You start from a group, you ask for its representations, you ask for character tables, you calculate whether it's irreducible or not, you ask for the outer automorphism of the group, which connects representations, which is another subtlety in classifying different order parameters, different CFTs. But anyway, GAP is powerful. You work on with it, you can finish this. So that's all I want to see, and thank you very much.
Well, thank you very much, Junchen, for the fantastic talk. And are there any questions from the audience?
Yeah, sorry, I hope I didn't misunderstand, but okay, so now if you're doing this for 05 as well,
yeah,
are you again finding kind of a line of fixed points that corresponds to the Ising CFT?
Yeah, okay, so maybe I tell you what we found for 05. You would already notice what the result is. So I mean, for 05, you are going to find the 05 Wilson-Fisher. You are going to find the cubic 5. I mean, we physicists call it cubic 5, but for mathematicians, this is signed permutation group with 5 elements. Okay.
Cubic 5 with cubic lattice, the Greek group.
Yeah. So permutation group is permutation group of 5 elements. Sign permutation means that you can flip the sign of each direction also. So this is what people call sign permutation group, but it's like cubic 5. The third one you find is like S6 times Z2. This is direct product. 6 is a permutation of 6 dimension. The reason is also easy. This 6-dimensional permutation group has I think it's called standard representation is 5-dimensional. So that's why you have this thing. So in the end, this is a whole list of irreducible fixed points. And so we finished the classification of irreducible 5 points. If you are interested, you can do this one. There's a little bit of subtlety because of double covering, but it's not too difficult.
Are there any questions?
Yeah, for the O3 solution, could you briefly describe what the solution is?
Yeah, actually, okay, I forgot one more, but no, I didn't forget. Okay, O3 is basically that's it. The stable ones. I mean, when you do RG flow, you still have to see whether your fixed point is stable or not on the RG flow. So the stable ones are O3 and cubic 3, basically. I think.
That's even another constraint.
Sorry?
That's even
yeah, so stability is another constraint which I didn't discuss, but sorry. But these are the stable ones. If you consider also on the non-stable ones, you can, well, irreducible ones, you can have like 3 copies of Ising model decoupled together. So I think that's the list, if I remember correctly. Yeah.
Irreducible, stable one, yeah, 2 solutions.
I think for O3, yes, if I remember correctly.
But if you don't require it to be stable,
then actually,
there are more solutions.
yeah, there are more solutions. For example, for this one, you actually find 2 fixed points with this symmetry. one stable, one unstable. So they are inequivalent, but they have the same symmetry. Yeah.
Instead of unstable fixed point, are they interesting or they're not interesting?
No. I think in general it's actually interesting. One question is actually, I mean, we are doing it for my system. So the question really is, the final question is what's happening in 3D. As I said, Bootstrap may help us. But okay, so for example, nowadays, if I ask you what is the 2D correspondence of this one, does it survive in 2D? I don't know the answer yet. So really, I think the real question is what you continue in 2D, whether when you continue in 3D, whether they are interesting or not. So by interesting, the real interesting thing are the things that survive in 3D. So a lot of things can happen. So they might interchange their stability. That's why I'm saying that one of them might be interesting. Stuff like that.
Okay, so I propose to continue the discussion. Thanks again.